Okay, good morning, everyone. So, I guess the first order of business, we have an exam Thursday. I think I told you Thursday, right? I'm getting all my classes bled together in my head, but I think I got that one. Do you have any questions about the exam? Cover everything since the last exam, similar, hopefully, in difficulty and format to the last one. Everything since the last exam through whatever we get through today. So, it's a moderate amount of material, keep you busy. So I wouldn't expect much change over the last one. If there's any, it's just like the last one. If there's any equations, I'll put them there, but I'm not going to explain them. I don't even know if I haven't looked at, I haven't made up the test yet, So I'll do that tomorrow, but I don't think there's any equations for you guys to go through. So I think we're good on that. Okay. So I think we ended up here last class. We're talking about groundwater flow. Again, just to set it up, groundwater is, at this point in time, one of our last good sources of clean drinking water, because we've polluted just about every freshwater source imaginable on this whole planet to the point where it'd be difficult, especially us living in the US, where we're used to clean water. Compared to the rest of the world, our water is right near the tops in terms of cleanliness. So we get used to that. Microbes in our stomach get used to this nice clean water. That's why if you go to other developing countries and drink the water, you can get really sick because you don't have the microbes to process that stuff. But the people who live there drink that stuff every day and they're able to handle it. Some water, though, is so bad that it doesn't matter where you live or what you've been drinking, it's going to make you sick. And they're really having those sorts of problems. Places like India, China, Southeast Asia, where the populations are growing quick, lots of pollution, and not good sources of drinking water. Problem is, we are extracting groundwater at a much greater rate than it's being replenished. Much greater rate. And in your lifetime, there are going to be problems. Starting to see problems already. Places like Denver, they can't get enough water. So what they're doing is they're going out into the prairie of eastern Colorado and they're buying up ranches. And they're buying up ranches not because the city of Denver suddenly wants to become a ranching community. They want the water. So they're buying the ranches just for the water rights. And then they're sucking the water out of the ground. They're shipping it in pipelines to Denver and Broomfield and all these places. So we're actually sort of de-ruralizing the rural areas. You're seeing people selling their ranches and the land just sitting there while Denver extracts the water. But they're extracting it at a greater rate than it's being replenished. So even that is going to come to an end sometime. We're going to have to deal with water in this country at some point. It's one of those things where, as it turns out, we don't pay for water what it's worth. It's heavily subsidized. You guys have, if you own a home, you pay your water bill. And, my water bill's over in Fort Collins, 60, 70 a month in the non-summer months. And then sadly, it goes up to about $200 a month in the summer while I water the lawn that I don't want to cut. But if I really paid what that water is worth, I'd probably pay 10 times. I can't imagine paying $2,000 a month to water my lawn. I can tell you right now, I wouldn't do it. The thing would be a big pile of rock. And that's where this is going, though. At some point, we're going to have to pay for this water. We're used to getting it really cheap, even though it's worth a lot more. And as it starts to run low, you see a lot of communities doing this already. They're doing what's called tier pricing. You get so much water a month at a really cheap rate. That way, if you're not making a lot of money, college students, you're poor, you're not getting hit with these ridiculous water bills. But at some point, there's some level that they say, if you go above that, you idiot with the big lawn that you don't want to cut, it's dumping water on it every other day all summer, you're going to pay, and you're going to pay big. So you're seeing tiered prices where certain first amount of water is cheap and affordable for everybody. But then beyond that, you're going to pay big. And it's going to change the way we use water, which is a good thing. But you will see this easily in your lifetime. We're starting to see it already. So we're going to talk about groundwater. We talked last class about how groundwater moves in the subsurface. It moves through cracks and pore spaces. This diagram here is showing you the general direction of water flows from upper right to lower left. But the actual path that a water molecule might take to go around all those little rock pieces is pretty convoluted, and it takes time. Groundwater moves pretty slow. You see a stream and it moves at a walking speed or faster. This stuff is pretty glacial. Shales, it might only move an inch in a year. In a sandstone, it could move across this room in a day. So it depends on the porosity and permeability. All right, there's a bunch of terms here. I'm just going to give you a minute to sort of copy this down. And then we'll go through the various parts. This diagram, I hate it. I hate this diagram with a passion. But I actually like putting it up because I can show you all the things that are wrong with it, and I think you can learn from it. This is actually from a geology textbook, which just irritates the crap out of me. Anyway, go ahead and do the notes, and then we'll talk through it. Looks like most of you are finishing up your notes here. So there's a lot going on this slide here. So let's just sort of break this down. Let's look at that diagram, okay? So you can see this is a diagram of somewhere on Earth. There's the Earth's surface. Right here, you see the trees, right? Growing in this stuff here, which is probably soil, even though it's not listed. So that's soil. Broken up rock and plant fragments. Soils tend to be pretty porous and pretty permeable compared to rock because they are broken up. And then down below it, doesn't really say, but this is rock, okay? Now remember, rocks have about, on average, maybe 5 to 15% pores. Some are less, like shales might only have 1% or 2. Some sandstones can be 20% or more, but we're talking 5 to 15%. So if your rock is 5 to 15%, what's 90 to 95%? It's rock, right? And this is colored brown to look like rock. But what it's not showing are the pores, right? 5 to 15%. And it's what's going on in the pores that matters for groundwater. So you can see that this area in brown is termed the unsaturated zone. Now, unsaturated means what's going on in the pores, not the rock itself. So in the pores, it's unsaturated. It's not saturated with water. In other words, the pores are filled with both air and water. If you dug down there and took the piece of rock, it would be damp. You know, it might feel a little wet because there's some water in there. But in each of the pores, there's a little bit of water and a little bit of air, okay? So think about it this way. Let's say you were right here and you drilled a well. A well is just a hole into the ground. Let's say I went down that far. And what you do with a well is you try to suck stuff out of the ground through the well. It's like a big straw. All right, there's 3 things in that unsaturated zone. What are the 3 things that are in the unsaturated zone? What's most of the unsaturated zone? Rock. If you suck rock, is it going to move? No. What else is in the unsaturated zone besides rock? You have pores, and in the pores you have 2 things. You have air and, all right, so you have rock, air, water. You put a well down, you start sucking. Which of those 3 moves the easiest? The air. You're going to suck air. You're going to have a non-functioning well. Is there water there? Yeah, there's a little water in there. It's just that the air is also there and the air moves easier. So yeah, you'll get a big sucking sound, big sucking sound of air, and big sound of wasting money because you're not getting the water that you wanted. Okay? In general, as you go deeper and deeper into the earth, though, the amount of water sort of accumulates. Because up near the top, it can actually evaporate back out of the soil into the air. But at some depth, it's enough time for water to percolate down. And that's when we end up in this zone here called the saturated zone. And this is why I hate this diagram. What color is the saturated zone in here? It's blue, right? What does it look like to you? It looks like a big lake of water with rock floating on top. What is in here? What is most of what's in the saturated zone? It's rock, more rock. It's the same, in many cases, it's the exact same rock. It's rock. It should be brown just like the other thing. The difference, though, is what's in the pores. Only water. Only water. So there's only 2 things here, rock and water. So if you drill a well down into the saturated zone, there's 2 things, rock and water. you start sucking, what's going to move? The water. Okay? So the only difference between these two zones is the degree to which water exists in the pores. If the pores are completely filled with water, that's part of the saturated zone. If there's some air in your pores, that's unsaturated. And that's where this third term comes from, the water table, which is a term I think most people have heard, maybe don't understand. You can define the water table a bunch of different ways. It could be the boundary between the saturated and unsaturated zone. If you think of this in 3 dimensions, you can think of it as the upper surface of the saturated zone. Or if you want a really practical definition, it's this last thing. It's the minimum depth that you need to drill to get a functioning well. Typically, when you're drilling, you want to go a little past the water table because the water table can fluctuate a little bit. And if you just drill to it, tomorrow area might be a little drier and you'll be in the saturated zone. You'll be sucking air. So typically you drill a little past the water table so that you're well into the saturated zone, so that you have a good, reliable source of water. Now you have to balance that practically with economics. It costs about $20 a foot, sometimes 25 to 30, to drill a well. So every foot you go down, you're going to spend 20 to 30 bucks. And especially in the West, a lot of areas have water tables that are 600 feet, 1,000 feet, 2,000 feet deep. So if you have to drill 1,000 feet, it's going to cost you $20,000 to $30,000 for a well. That's not a small chunk of change to anybody. You buy a house for $300,000, you could spend 1/10 of it just on putting in a well if you're not in a city. It's substantial. So again, groundwater does not flow in underground lakes or rivers. Does not do that. Even though this diagram makes it look exactly like that. Here, I'll help you. You get the point though. Saturated zone, pores are filled with air and water. Unsaturated zone, pores are filled with water. Both zones are mostly rock. The water table is the boundary between those two zones. Okay. See what else we have. Any questions? Okay, so the unsaturated zone again, air and water. This is sometimes called the vadose zone, zone of aeration. If you have a textbook and you're reading about this, you might see those two terms. Most people, I think, call it the unsaturated zone. Then the saturated zone, that's where the money is. That's where the water is. That's where you want to drill so that you have a functioning well, because you have just rock and water will move easier than rock. In the unsaturated zone, the air moves easy. Boundary between these two is the water table, or you can think of it as the upper surface of the saturated zone, or the minimum depth needed to form a functioning well. And then there's our crappy diagram, unsaturated zone, saturated zone, and then water table in between. Okay. Again, a little science background before we get into the human use of this stuff. Water movement, unlike surface water, is typically really slow. Shales, we're talking a couple of centimeters, an inch or so in a year. If you have loose sand along a river, could move 100 meters a day, a football field. Very porous, very permeable. Most of the times we're talking a centimeter a day, a couple centimeters a day. So, think about inch a day. Glacial. It moves about as fast as a glacier. This is a feature that's kind of important too. Most of the times when we draw these diagrams, we show the land being sort of flat, but you go out into the real world, you know that the surface of the earth undulates. Well, the water table tends to mimic what's going on the surface above. So if you're on a hill, the water table will be up higher. If you're in a valley, water table will be down lower. And I'll show you some diagrams of that in a minute. And then this probably makes perfect sense to you by now, but the velocity, the speed of movement of groundwater depends a lot on the permeability. If you have a really permeable rock, pores that are connected, lots of pathways for the water to travel through, as your permeability increases in general, so does your speed of water movement, your velocity. So as your permeability P goes up, your velocity V goes up as well. What also affects it is the slope. And even though I don't like to make comparisons between groundwater and surface water, in this particular case, it might be useful to compare the two. So think of a stream. So if a stream is moving along, let's say it's traveling down the slope of a couple degrees, it might just be sort of moving along. Then if it hits a really steep spot, what happens to the speed of movement? Think of it over a waterfall. Speed gets really fast, right? So the steeper the land that the stream is flowing over, the faster the water is going to move. It works the same way with groundwater. If you look at the slope of the water table, where the water table is steepest, water is going to move quickest in those areas. And again, I'll show some diagrams here shortly that will hopefully illustrate that a little better. And in a couple of terms, I'm guessing all of you have heard the term aquifer. If not, no big deal. But an aquifer is simply a body of rock, or I guess soil too, that is saturated and easily transmits groundwater. So good aquifers are things like sandstones, which are really permeable, limestones, which are really permeable. But some areas don't have any sandstone or limestone. If you go up to, say, the Rosebud Reservation in central South Dakota, pretty much everything that lies beneath the reservation is shale. Different kinds of shale. You have this shale, and you have that shale, and you have this shale, and you have that shale. And all these shales only have a few percent porosity. A few of them are a little more permeable than others. So you would probably say the most permeable shale in that area is the aquifer. That's just the best rock you have beneath you for groundwater. Now, if you move that rock here, where we have sandstones or shales, it's like, no way I would drill into that because they have all these other rock units that are much better. So there's no strict definition that says an aquifer has to have so many cent porosity or so much permeability. It's more of a practical term in each area. Which rocks most easily transmit groundwater in that area? Around here, we would never use shales because we have sandstones and limestones that have lots of water. Water flows through real well. But if you live on the Rosebud Reservation, it's just, do I pick this crappy rock or do I pick that crappy rock? Because it's all shale. Yeah, they have real problems there because not only do they have shales, but the water that's in them has a really high mineral content. So the water tastes terrible. If you try to put soap on, it doesn't lather up because there's so much stuff in the water already. It's kind of an awful mess. So these are typical rocks that you would look for aquifers. Like I said, sandstone and limestones are rock units that have good pores and good permeability. But sometimes you don't have sandstones or limestones in the area, especially if you're up in the mountains. If you're up in the mountains, you're just sort of over igneous granite rocks, which have really crappy porosity and permeability. So then what you would look for are areas that are fractured, where mountain building has broken up the rock and water can flow through it. Or you look for places where the rock has broken up and accumulated in low spots. We call this alluvium. If it's by a stream, it's part of the sediments that the streams flow through. A term I don't have up here is colluvium, and you don't have to write it down, but it's kind of like landslide material. It's rocks that have rolled down the mountains. So we have a place over in Steamboat. It's outside of town. It's up on the side of a mountain. All the rock beneath us is igneous rock. It has essentially no pores at all. And yet we need water out there. And there's like 10 houses in the area, and they decided to share a well. And they looked around, and what they found was a big patch of fractured rock that had loose material on top where rocks have rolled down for thousands of years. And they basically drilled into that, and it's just enough so that water can accumulate in enough abundance for about 10 houses. Water quality is really good because it's just snow runoff, but you could never provide enough water for like a city from a small patch of broken rock. But it's enough, so that we each use our 20 gallons a day or so, and it's good. But if you have sandstone or limestone, that's even better. This last term, perched aquifer, kind of an important term, and it's important in certain areas, especially here in the United States. Its definition is, I think I have it here. It is a small patch of saturated rock or soil that lies above the main water table. Okay, so this diagram is a little better than the last one. So it shows the unsaturated zone here, rock mostly, and then in the 5 to 15% pores, it has water or air. And then down here, this is a little better diagram of the saturated zone. It is colored blue, but if you look close, you see the little dots. They're at least trying to show the rock. So again, that's mostly rock, but it has pores. The pores are completely filled with water. The boundary between these two is the water table. Now, in general, you want to drill down into the saturated zone for a well, right? But it's $20 to $30 a foot. In some areas, especially in the Midwest of the US, there are rock units that say are mostly sand, but they have like little clay or shale units in it, like right here. And what will happen is the water will soak down from the surface and get ponded on top of that impermeable shale or clay layer. And then the rock and soil that lie above it will get saturated. And sometimes it's enough for a household or two, just like I was talking about with our place. And in this case, you only have to drill down into that to get water. So perch water table is a smaller saturated zone that lies above the main saturated zone because of an impermeable rock unit. So the thing is, you don't know if you have these under your ground. Just that the driller will be drilling and all of a sudden he goes, oh, got some saturated rock here. We're 400 feet above where I thought we were going to have to go. Good for you, bad for me. You know, so this can save a homeowner a lot of money. Drillers don't like it because it saves the homeowner a lot of money. And then another term here, a spring is where the saturated zone meets the Earth's surface. Basically, water just pours out onto the ground. In this case, you're seeing it from a perched aquifer, but there's some places where the main saturated zone will do this too. Now, the depth to the water table varies in different places. Like I said, here out west, it could be 1,000 feet. My dad lived in Wisconsin, northern Wisconsin. He had a place out in the woods. You could get to the water table with a shovel. It's only about 4 feet down. He didn't have a basement for that reason. You don't want a basement if your water table is only 4 feet down, or you're going to be constantly pumping water out of your basement. So, yeah, he had a pond like 20 feet off his back, and that was soaking into the ground. And so, yeah, you could just hand dig down to the water. And in some places, they do that. I've been to places in Africa where local communities have hand dug wells that are 500 feet deep. And then they'll lower a bucket down, just like you see, and the water will accumulate, and they'll pull it out. And sometimes people and animals fall in, and it's a real mess. You know, here we're a little more developed with our technology. We drill wells and then put pumps to get the water out of it. Yeah, just by luck, because you can't see it, right? Because you're up on the surface. So, you know, let's say you have a piece of property and you're going to put a well on it. Normally, you'll want kind of an estimate. It's like, okay, how much am I going to spend for you to drill my well? And the driller will say, well, your neighbor over there, he had to drill down 600 feet. And your neighbor over there had to drill down 580 feet. And that neighbor over there had to drill down 590 feet. So you're looking at about 600 feet. And then they start drilling, they go down 200 feet and they hit saturated rock. And it's like, good for me. You know, you don't know how big it is. So a lot of times they'll test it, see how quickly the saturated zone lowers. And they'll say, yeah, it looks like there's enough for a single household. Or, you know, there's not much there. We're just going to have to drill through that down to the bottom. So you don't always know. So the depth to the water table can vary. The depth to these perched water tables can vary. Sometimes you can get a configuration with the rocks and groundwater where the water becomes pressurized. I think I have a diagram to show that. And so in this case, if you drill a well right here, you're going to have water that rises to this level in your well. Okay, it's going to go right to the top of the set. That's the level. If you're in an area where the water is under pressure, the water will rise up in your well, and sometimes it'll just pour out onto the ground, which is great because then you don't have to pump it. And those are called artesian. Anytime the water is under pressure and the water either rises up, if it goes all the way to the surface, then you have an artesian flowing well where it naturally flows out onto the surface. Those are the best ones to have. You just drill a hole and you never have to pump. Here's an artesian system. So just to sort of set it up, so you got this rock unit right here, which is impermeable, something like a clay or a shale. And then beneath it, you have an impermeable rock, a clay or a shale. And sandwiched between these two is a nice permeable aquifer. Now that aquifer is recharged over here where this rock unit is exposed on the surface. So anytime it rains on there, that water soaks into the ground, okay? If you drilled a well right here, your water level is going to rise to the water table, which is right there. But as you go down into this rock unit, this water all becomes pressurized. We're not going to get into why, it just does. It actually is going to want to rise to about that level right there. And you can see here in this area, it rises partially up your well. You still have to pump it, but it gets close to the surface. In this area, this water will actually pour out on the ground. There's enough pressure. Now, if a lot of people stick wells in here and start sucking the water out, this water table is just going to keep dropping, and eventually these artesian wells won't be artesian anymore. So that can happen as well. So an artesian system is just one that has pressure and forces water to flow up into the well. Typically an aquifer sandwich between two impermeable clay layers, and it's that sandwiching that gives rise to the pressure of the water in the aquifer. Second term is something called an aquiclude or an aquitard, and they're comparatively impermeable when put in contrast with aquifers. So these are things that you really don't want to drill into. They're not going to provide you with enough and a steady enough supply of water. Okay, any questions on background terms? Okay. All right. That's the background. Give you a little mental picture of what's going on in the ground. Remember, it's all rock down there. 90%-ish rock. And there's some openings in the rock. Some of those openings will have water and air. Some will just have water. Now, groundwater is a really excellent source of water for people in most cases. As water moves through the ground, through those pores, a lot of the impurities that it has in it gets filtered out by the rock. The rock acts as a big filtration system. So groundwater tends to be pretty clean, especially compared to surface water, especially if the water's been down there a while. Sometimes the water's been down there hundreds of years. And if you have a clay layer on top of it, then whatever we do on the surface can't soak down in the groundwater very easy. That clay layer protects it, which is really great. Now, we can pollute groundwater, sadly. In fact, we do it all the time. And the closer it is to the surface, the easier it is to contaminate. I'll digress here for a second and give you an example. So I'm going to draw a little diagram here. So there's the Earth's surface right there. And let's say we have a place where we have a gas station. Gas stations all over here, right? So where is the gas held at the gas station? You just go up and take the pump handle, right? And gas magically comes out of it. But where is that gas? It's in big tanks underground, okay? So beneath the gas station is a tank filled with gas. Usually they're made of metal. They can be made of plastics. It doesn't matter what they're made out of. They don't leak until they leak. And eventually they leak, especially if they're metal and stay in the ground years and years. Because remember, the ground is sort of wet, right? So let's say here is our water table. Okay, so this is the unsaturated zone. This is the saturated zone. Let's say gasoline leaks out of this, okay? Gravity's going to pull it down, right? Let's say the groundwater in general moves that direction. When the gasoline finally hits the water table, where does it go? Will continue to sink into the ground. What happens if you dump gasoline on water? It floats, right? So what will happen is the same thing will happen there, is that the gasoline will tend to move right on top of the water table. Remember, this is unsaturated though, right? What's in the pores? Air and water. If you dump gasoline on the driveway, what happens to the gasoline you dump on the driveway? It's what? It stinks. Why does it stink? It's evaporating, right? I mean, you ever see how fast gasoline evaporates? You ever have gasoline on your hand? It feels cold because it evaporates so fast. It evaporates when it comes in contact with air. Is there air in the unsaturated zone? Yeah, this will actually start evaporating into the soil. So you will have gasoline fumes in the rock and soil. How do you clean that up? Can you pump it out very easy? It's pretty tough, right? Yeah, once you contaminate this, it stays contaminated for a long time. Usually what they have to do is go in and just dig up massive amounts of soil that have been contaminated by it. Now, if you spill other liquids that are denser than water, they will continue to sink down maybe until they hit an impermeable layer, and then they pool up down here. So there's a whole science of contaminants in groundwater based on their density and how easily they evaporate. Fact remains is that once you pollute groundwater, it's really hard to clean it up because it's in the ground, doesn't come out easy. You get all this evaporation stuff going on. So the deeper it is, the farther it is from human contamination, the better it tends to be. So a well is what we use to actually get the water out of the ground. But the thing is, the minute you start pumping water, it changes everything. I'll show you why. It creates a feature that hydrologists call a cone of depression. A cone of depression is a change in the shape of the water table. And it occurs when you pump water out of the ground faster than you can recharge it. Some of you have water bottles in front of you, okay? So if you put a straw into your water bottle and start sucking water out, what happens to the water that's in the bottle? It goes down, right? But it goes down evenly, right? The whole surface of the water will just start going down, down, down. So you drink all the water out of it. I've been drinking on this Mountain Dew for 2.5 hours now. The level keeps going down, but it's nice and horizontal, right? That doesn't happen with groundwater. The reason it happens so well with this, you put your straw in the middle and start sucking, the water fills up the voids because it moves around easy, right? Water in the ground doesn't move easy. So when you suck water out from a well, you tend to take the water that's right near the well, and then it takes some time for the water to sort of fill up what you sucked out. And what it does is it creates a local lowering of the water table in the shape of a cone in 3 dimensions. I'll show you a diagram here in a second. And it's these cone of depression effects that geologists deal with a lot. And the thing is, if you pump too much water too quickly, you can actually make your own well go dry temporarily. You can basically suck all the water out of the ground that's right near the well. Then you have to sit and wait for water that's a little farther away to flow back towards your well. raise up the water table, and give you a functioning well again. So it works something like this. Let me see if I can draw a diagram. So here's the air surface, right? And I'll use purple since I have a blue background. There's the water table. All right, you put in a house out in the country, you need a well, right? Got to drill down, get some groundwater. What if I drill that far? I have a well of air. Yay. Not good enough, right? What if I just drilled right to the water table? Any water I suck out, I'm going to lower the water table right there, and it's going to go dry right away, right? So you just want to go a little past. Sometimes you want to go way really far past, but you go a little farther past. If you don't pump, what'll happen is the water will rise in the well to this level. Okay? You threw something down, it would fall, and would splash right there. Okay? What if you start pumping? This water level will lower, right? And yet, what'll happen is the water table will respond to that as well. It'll look something like this. It'll be lowest right by the well, and at some point away, the groundwater doesn't feel that you've pumped yet, okay? And what'll happen then, let's say you pump it down to here and then you stop pumping, okay? What'll happen is you've created a little slope right here, right? And the water will move and it'll start filling this up again. And if you give it enough time, it'll fill all the way back up. Then if you start pumping, you lower it and you create this cone of depression. Because in 3D, it looks kind of like a cone. Okay, so that's the cone of depression. It's a local lowering of the water table. And if you pump too fast, let's say you pump a lot, you could make a cone of depression that's, say, this big. Your well can go dry temporarily. You have to wait for the water table to start to rise in this area, water to come in and fill this back up. So it goes down, it goes up, goes down, goes up. Yeah. Depends how permeable your rock is. So if you have like loose sand, it could fill up in hours. If this is a shale, you might have to wait 2 months. You might have to wait a year. So it really depends on how permeable your rock is and how deep your well is and how big your cone of depression is. Sometimes your cone of depression will only extend out 20, 30 yards. There was a case in Arizona in a northern suburb of Phoenix where a whole area built up outside of town. They all had their little wells. You know, they all drilled 30 or 40 feet past the water table. They all had nice, stable supply of water. And then they put a golf course in. And the golf course put in a really deep well, pumped a crap ton of water out of the ground, made a cone of depression that was so big that everybody's well went dry. Nobody had water for a while because it extended out a mile or more. I'll show you some diagrams here coming up. And this is what we're talking about right here. Not only might you cause your well to go dry, which is bad, you could cause your neighbor's well to go dry, which is arguably worse. Depends what you think of your neighbor. It could be your problem too, because if they prove that your well is the culprit, you might have to pay. This is actually one of to me, the more interesting and lucrative careers in environmental science is water law. There are conflicts. There's so many conflicts with water that Greeley Courthouse has one day every month that's devoted just to water. They call it water court. They have a special judge that only deals with water issues. The judge has a science background, understands how water moves in the subsurface. And lots of scientists come in and testify, and people like, your well caused my well to go dry, and now I can't provide my cows and chickens with, and you're costing me thousands of dollars, and I'm going to sue your ass. And it's like, you can't prove it was me. And it's like, yes, I can prove it was you because I got these scientists. And that's what happens at water court all the time. People fighting over the amount of water that each other is using. So it gets really serious. And if you're a lawyer in this area, you're going to do really well. So here is an example, okay? So in this top diagram, you've got Joe Farmer, Jolene Farmer, whoever it might be. They have their well, okay? They have a well here. They have another well here. Notice they didn't put their wells very deep because they are not huge water users. They know how deep they need to go. If you look closely, you can see here, there's a little cone of depression, right? So they're pumping some water. Over here, you're not seeing much pumping, so there's no cone of depression there. But then let's say the Denver comes in and buys your neighbor's ranch, and they do it for the only purpose of sucking the water out of the ground. And they know they're going to suck the water out of the ground. So they drill a really deep well, and they start pumping, and they start pumping, and they pump, and they create this huge cone of depression. Is that well going to pump water? It did before, lots of water. Now it pumps air. Why? Because of that. The problem is, can you see any of this? So how do you prove it? You can't see it. It's really difficult to prove in court, isn't it? Well, luckily, the science has progressed to the point where if you know how much this person is pumping, and you know something about the nature of the rock here, you can actually calculate the size of the cone of depression. Now, Joe and Jolene Rancher can't do that. They don't have the science background. So what do they do? They hire me first, hydrologist. I do these calculations for them and say, yep, City of Denver's well created a cone of depression that's 2 miles wide, lowered your saturated zone so much that your well is dry. And they weren't supposed to do that. And I'll go to court and testify. But I'm not going to do that out of the goodness of my heart. I'm going to do it out of the goodness of my wallet. So Rancher there has to pay me to get the science to set up the lawsuit. And then Rancher has to pay Joe Lawyer or Jolene Lawyer to go to court and argue this. And then what's Denver going to do? They're going to do the same thing. They're going to hire their hydrologist and say, no, you made a bad assumption about how permeable the rock was. That's why you need experts. Who makes money? The experts and the lawyers. Who loses money? Sadly, the farmer loses money. So this is important. I mean, that farmer has no water. They have 2 choices, right? What are their 2 choices? I guess they have 3 choices. And deeper, which is expensive, sucks, right? Maybe they have to spend $25,000 for a deeper well. They could move. They could sell their ranch to Denver, and they said, fine, you win. Or they can fight it. And they'll have to do the math. It's like, I got to pay Anderson $18,000 for his services, and I got to pay this lawyer $35,000. It's going to cost me $53,000 to go to court, and I still might lose. Yeah, you know what they'll do? They will buy one of these big 500-gallon tubs that you can put in your truck. They'll drive somewhere, they'll fill it up, and they'll have to live out of that water in the back of their truck for a while. It happens all the time. You see that a lot with people in rural areas. They will truck in water when they run low on their well. Sometimes pumps fail. I mean, you might not even have a problem with the amount of water. Your pump might fail. It might take you a month to get a new pump set up. You need water, right? You can't go a day without water. So you have to go somewhere and fill up a big tank. We don't worry about that in the city because why? We go turn that little handle over there and water just comes out. We never think about the amount of water when we're in a city because we have these services that provide us. But if you're out on your own in ranching and farming country, you think about this a lot. So cones of depression, serious issues. This is one of my favorites, though. I love this one. It's disgusting. My example is disgusting. That's probably why I like it so much. All right, I'm gonna draw again. And let's say there's the surface of the land, okay? And your property goes from right here to right here, okay? That's your property. You live out in the country, okay? You're not in the city, you're out in the country. So you need a house. And you decide after looking at your place that I'm putting my house there. You need two other things. You need more than two other things. But with respect to water, you need two things. You need water, right? You need a well. And then you have to have somewhere to put your wastewater, okay? You flush it, it's got to go somewhere. When you're out in the country, it's not going to go to some sewage treatment plant. You have to deal with it. Anybody know how we deal with that in rural country? It's something called a septic tank, okay? It's basically a tank buried in the ground that all your wastewater goes into. It accumulates. All the chunky stuff sort of settles to the bottom. The cleaner, but not completely clean water sort of flows out the top into the soil. And then as it moves through the soil sort of filters away all the stuff. First, before we get there, though, where's the water table? What does the water table look like? We don't know how deep it is, but what's the shape? It follows the surface, right? So the water table might look something like this. I want you to decide where's your well going to go and where's your septic going to go. Which direction is the water, groundwater, going to flow in this area? Remember, it flows with the slope, right? So water is going to flow like this. All right, you got to put in a septic and a well. Where are you going to put your septic? What's that? You want it over here, right? There's your septic. Why did you put it there? I agree with you, but why did you put it there? So if this leaks, it's not nice stuff, right? This is something you flushed down yesterday, okay? So if it leaks, it's going to percolate down, right? And then it's going to move away in the groundwater. So where's your well going to go? So you're going to put your well here, right? That's what I would do. Is it all good? What didn't I account for? What happens when I start pumping? What am I going to make with respect to the water table? Cone of depression, right? What if my cone of depression looks like that? Now the water goes down. Where does it go? Sadly, you've changed the direction. And it's a deadly cycle, right? Fact is that your septic system can contaminate your well if you create too big of a cone of depression. Now, if your neighbor's down here, it can suck to be at the bottom of a hill with respect to water, because everything that people do up above you, it's like living downstream. You know, what people do upstream will affect you. With groundwater, what people are doing uphill affects you. So actually, I think I drew this out. So there's the house. There's another house. There's your property line. Water table will mimic the Earth's surface. So you put your septic tank and your well in. Like you said, we're going to put the septic down low, put the well up a little higher. But if your well creates too big of a cone of depression, you change the direction of your water movement. And now this stuff, percolate down, percolate over, and you suck it back out. This is really common. So, like I was telling you about our place in Steamboat, the well is at the highest point above everybody's lots. It's actually about 200 feet above our house. So we don't suck enough water out of the ground for the cone of depression to start changing the direction and sucking everybody's septic effluent into our well. So this is something that people give a lot of thought to when they put in wells. How big is cone of depression going to be? Where are people dumping their wastewater? Not good for you. Another example here where your septic effluent normally would go a different direction, but because you're a large water consumer, you change the slope of the water table because of the cone of depression. Like I said, being downhill has its hazards. You have to be aware of what's uphill from you if you live in well country. You know, here in the city, no big deal because we're getting water through pipes from water towers and things like that. But out there, everybody's just tapping into the ground for the water. It's not coming from a central source. All right, I'm going to finish with this. This is a big problem. It's a big, big problem. This actually goes back to one tiny little tidbit that I threw at you back when we talked about water 2 months ago. Remember, I talked about the structure of the water molecule, and we were going, water does this and water does that, and it's, got these dipoles, and we talked about all these different properties of water. There was one property that I threw at you. We didn't talk about it much, but it's important in this situation and a big deal, and that's that water is not compressible. Water doesn't squish when it's under pressure, okay? So deep in the earth, all right, we have pore space, right? And in the saturated zone, where we want to go to get our water, the pores are only filled with water, okay? But remember, that's in the ground. And as you go deeper in the ground, what happens to the amount of pressure from the overlying stack of rock above it? Greater, right? So if you have an opening and you have a lot of pressure, the tendency is going to be to squish that opening, right? What if you have water in it, though? Water doesn't squish. It doesn't compact, so it acts as no different than the rock, right? Because the rock's not going to compress. It keeps it open, right? So the water is keeping the pore open. But what happens when you start sucking out groundwater? You change the slope of the water table, right? Which means you're making new unsaturated zones. The minute you take the water out and it's just air compacts really easy, right? So let's say there's a rock, the green, and then you have pores filled with water, the blue. That's deep in the earth. So you've got lots of pressure that want to close those pores, but there's water in it. So the water acts as a support. And that's what you're sort of talking about with the sand. It supports the fracture. This supports the pore, yeah. Well, okay, so the next part of this is that if you take the water out, those pores are going to start squishing, right? If, let's say, you do it over a big area and you suck a lot of water out, the whole Earth's surface can start to collapse because of all the pores that are being squished underneath it. So let's say, I don't know if I have a good, I'll get to a diagram here in a second. So you can start to compact your aquifer. One bad thing is if you compact the pores, can it ever be a good aquifer again? You can ruin your aquifer by sucking water out of it because the pores collapse and then there's nothing for new water to go into. That's bad. The other thing is that if you collapse the pores, just think if this had 20% pores and you collapse them all. That's 20% less land that was there before, and your land surface is going to start to drop. But it's not going to drop evenly. It's going to drop mostly by your well, right? There's stuff in the ground. As humans, we love to put stuff in the ground, like gas lines. We don't put gas lines on the surface because people cut them and we bury them to protect them. What happens to a gas line if suddenly your area is collapsing? The gas line's going to bend and can eventually break. Water lines can bend and break. If you have a house over the area, your foundation can shift and you can be the crooked man and crooked woman in a crooked house. It can be really bad. This is my favorite. So this is the interior San Joaquin Valley in California, where a lot of our winter vegetables are produced. So if you've been to this area, it's dry. It used to look like what the prairie looks like out here, sagebrush. It only gets 10 or 15 inches of rain a year. But the rest of the climate's really nice for growing, so they suck groundwater out in massive amounts to grow food. And as they're doing it, the water table is dropping. You're creating more unsaturated zone. Those pores are squishing. This actually shows where the land was in 1925. And then there's where the land surface was in 1955. And then this was 1977. Today it's probably down there about another 50 feet. So the whole area is just sinking a lot. And they just put this pole up to illustrate where the land surface was before that. So the other place where this happens a lot is in coastal areas. You know, coastal areas, oh, lots of water, but it's salt water. So places like New Orleans, what they're doing is they're sucking water out of the ground. That makes the whole area sink. What's happening to sea level with climate change? Sea level's rising. What's happening to hurricane situation? We're getting more of these, right? So places like Louisiana are sinking while climate change is making the oceans rise and while bigger storms are coming in with these storm surges. And they're also putting up levees that don't allow more sediment to accumulate. They're just sinking all the time. And this is one of the reasons, is they're collapsing the pore space in a lot of the wells that they're using for water. Yeah. Once they collapse, no. That aquifer is done. You'll never be able to make the surface rise back up. So a lot of places on the coastal areas are doomed. They are doomed. They will eventually be returned to the sea. And this is one part of that. There's a lot of parts. Sea level rising, no new sediment on the deltas. Lots of people live on deltas because there's fresh water coming in. It's a great place to live. New Orleans is right on the Mississippi Delta, but they're sucking water out of it. It's sinking. Sea level's rising. Big storms are coming in. It's going to be a mess. You're going to hear about New Orleans a lot next 20, 30 years. I would guess in maybe 50 years, might not be there. They'll get hit by 2 or 3 hurricanes in a row, just buries the town in water. People will start moving out. That's what we're talking about with mass relocation due to climate change. You get hit by one storm, you recover. You get hit by 4 storms in a row, and it's like, I can't do this. So that's going to probably be the future of those areas. Okay, let's end there. We'll finish this up next week. Test on Thursday. You have any questions? I'll be around tomorrow writing the exam, so it's a good time to get a hold of me.